Hi everybody, today we're going to talk about one of the most popular data structures that we use regularly without actually realizing we may be using them. Whether you're surfing the internet, searching for something using Google or any of the popular databases that might be used by your applications, there's a very good chance a Bloom filter is being used behind the scenes. And it's not just for data, it's in cryptography or even very common situations where you have a large amount of data and you have something that needs to access it. It could be an e-commerce site, could be a registration form, it could be a billion different things. And so in this video, we're going to learn all about what Bloom filters are, how they work, what makes them so efficient and useful and popular as a result, and a variety of other details that you will probably need to become very good at using Bloom filters in whatever it is you're trying to use them for. So in our example, we have a very popular social network and it's called Petbook. One could imagine that Pixel over here could be a member of this site. Now, as part of using Petbook, there's a registration step, and this registration requires you to pick a username. And the one criteria is that the username you specify must be unique. And so if you have a username that's unique, great. In this case, Inji is a unique username, so you can register and you're happily on your way. But if you're using a name like Pixel, the username is not available because it already exists, so you cannot pick that name as part of the registration. Now, let's imagine that because this network is very, very popular, we have a giant database of usernames. In a world without any optimization, what would we need to do? Then I'm typing in a username in the Petbook registration form. I go to my database. I ask the question, does username exist? There's something that runs across the database, and I get a yes, the username exists, in which case I can't register. Or I get a no saying, nope, the username does not exist. You have picked a unique username. Congratulations. You can go ahead and register. Now, the thing is this. Because our database is part of a very popular social network, we can imagine that a list of existing usernames, the amount of data that's already in it, is very, very large. And as part of making a good user experience though, we need to make sure our registration page is not slow. It needs to be very fast. The end-to-end checking needs to be fast and accurate. You don't want to be told a username is available and during registration you realize, nope, it actually isn't. So you need to make sure that at that moment we give you an answer very, very quickly. So let's take an approach where we want to scan all the entries. Let's say that I have a database. We can use an array or list-like data structure to store all of them, and then we can go ahead and see a value one at a time. It could be at the very beginning of the list, which case I'm very fast. It could be at the very end, which is slow. But on average, it gets set as big O of n time. It's linear. Now, because databases are also disk-based and there's maybe network activity, it's on the slow end of what linear really needs to be. So that's not exactly going to be great. Now, we can use a hash table. We know that there's a data structure out there that can very quickly tell us if something exists or not, given a set data structure. A hash table is absolutely perfect. Now, the downside is hash tables are too memory intensive. You have a lot of data. You want to store them all in the hash table. You're going to be taking up a lot of memory in order to make that work. And also, depending on your hash table implementation and how much data you actually have, it's going to come to a point where you may have collisions in your hash table. So that big O of one time, the constant time that hash table returns the result, it may actually be much slower. And that kind of defeats the purpose of a hash table sometimes. So what we really need is a fast and memory efficient solution to help us out here. What we need is the star of this tutorial, the Bloom filter. Now, before I get into the details of Bloom filters and how they work, I just want to take a step back and let you know that if you like to learn about data structures and algorithms at a much detailed level, but on your leisure in a book form, my best-selling book, Algorithms, Absolute Beginner's Guide, is just what you need. It's available in paperback editions, Kindle editions, and whatever new form of content consumption that gets invented by the time you're actually watching this video. And links to all of that will be in the description below. So getting back to our regularly scheduled programming here, I'm not the only one, but every time I hear the word Bloom filter, I'm always reminded of the classic James Bond villain who's been across many, many films, Ernst Blofeld. And for some reason it always reminds me of that when I think of Bloom filters. So I don't know if I'm the only one here. If I am, cool. If I'm not, feel free to comment below and just say that, yep, you're also someone who gets reminded of a Bond villain when you hear of Bloom filter. But anyway, getting back to the technical part of what I wanted to talk about. So a Bloom filter is an optimization layer. It's an optimization layer that stands between the thing that you're interfacing with, in this case a registration form, and where the data ultimately lives, where the source of truth actually lives. And this source of truth is often the slow things that you want to optimize for. So the Bloom filter really exists in the middle to kind of provide a way of, you could think of it as a caching layer, but it's a way of just speeding things up so that, you don't want to go to the very end as much as you want to. So whenever we need to check whether username is in use or not, the goal is to have our Bloom filter provide the answer. Only in a few cases should a slower database be consulted. So if you can bypass a slow database, we give you a fast answer, a fast path to being happy every single time. And so the goal really is we want to keep as many of the requests, between the pet book and the Bloom filter as possible. Only rarely do you want to go from the pet book to the Bloom filter to the giant database of usernames. That's a worst case scenario. We don't do that unless we absolutely have to. So how does our Bloom filter pull this off in a fast and memory storage efficient way? Arrays and lists and other linear data structures, they're not going to work. The hash table, the thing that we thought was going to be the answer to every performance question involving data, that's not going to be helpful either. When I say hash table, I also mean your maps, your sets, and other data structures that are built around it. And so the Bloom filter works in a very efficient way and in a fast way because it does not store the actual source data. And this might be more of an implementation detail, but I'm giving you a spoiler alert of what to expect just so you can get your head into the right space of how it's going to work. Because what a Bloom filter does, it stores a fingerprint of the data. It stores it in the form of a single 0 or a 1. And that's almost as lightweight of a value as we can get. Our computers are designed for zeros and ones, and storing it in that form is fast and very memory efficient. And somehow or another, all the data in our database or whatever data structure we're optimizing for in the Bloom filter is represented simply as a 0 or a 1. And here's how that works. So to make sense of all this, we're going to go through an example. And we're going to do a setup phase where we have a data, in this case, our database of usernames, and we want to have a Bloom filter represent all that data. There are 3 stages here. First, we need our initial data. Second, we need a bit array. And third, we need a number of hash functions. Not, just one hash function, but a number of hash functions. And we'll talk more about that number later. And these hash functions map each element from our data into an array position, the bit array. So more on that, but let's start with the first step, the initial data. In our case, we have a bunch of usernames in our database, but for just the realities of going through this video and the amount of virtual or vertical and horizontal space that's available on the screen, we're going to go with 5 values. The usernames that we have in our database are Ingy, Muffins, Bluey, Bingo, and Pixel. So we have 5 values. And then we have a bit array. So if you're not familiar with bit arrays, they're nothing more than just a plain array, just a regular array, and they function, they have all the right capabilities as an array would, but they're limited in what values they can store. You can either store a 0 or a 1. You can store a bit, essentially. Nothing else can be stored inside them. So they always have a very predictable set of things. They either have a 0 as a value or a 1 as a value. And with our bit array in particular, there are 2 details to note. One is when we initialize our bit array at the very, very beginning, they'll be initialized with 0 values. And the length of the bit array, this is something we'll talk more about in detail, but the length of the bit array plays a big role in determining how much data we have, but how accurate we want the data to be as well. So for our example of just 5 usernames of 5 pets, let's just keep it at this number. We have 11 values, index between 0 to 10. In real life, there'll be a different number. We'll talk more about what that number should be later on. The third step is we need some hash functions. What these hash functions do is they map the data in our data that we're trying to index, in this case a username, to an index position in our bit array. So you have username, then you have the values going between 0 and 10 in our bit array. And the exact number of hash functions you need is often something we can adjust, and that also has to do with how accurate we want our Bloom filter to ultimately be. And this is something, again, take it, put it in your back pocket. We'll come back to it in a few minutes when we talk about how do we optimize our Bloom filter. That's where the size of our bit array and the number of hash functions, all are things that we can control to get the final the Bloom filter result that we want. So to recap the 3 steps that we have here, we have currently at the very top, we have our initial data, which is Ingy, Muffins, Bluey, Bingo, Pixel. We have our 2 hash functions, which I'm representing as the blue robot and the purple octopus. Then we have our bit array at the bottom, all initialized to 0, and they have index position 0 to 10, so we have 11 values that we can go through. So now what we're going to do is we're going to go through each of these items and store them in our bit array. So the first thing is we want to store the value ing. For every value we want to store, the first thing we do is we pass it through all the hash functions that are currently available. In this case, the first hash function is going to be our blue robot hash function, and that hash function returns a value of 5. This 5 represents an index position, so we go to our bit array and we find the value at 5, which is initially 0, and we set it to a 1. The hash function has returned a 5. As I put it in the bit array, we set it to a 1. Now we have two hash functions, so now we pass the ing value to a second hash function, in this case the octopus hash function, and that returns a value of 7, index position 7. And so we go to our bit array, find a value at index position 7. If it's a 0, which it is because it's, we haven't done anything to that array yet, besides the 5, we set that value to a 1 as well. So each time a hash function returns an index position, we find its corresponding value in the bit array, and we make sure it's set to a value of 1. So that's a little bit faster. The next value you want to store is muffins. And for muffins, the two values returned by each of our hash functions is 0 and 6. The blue hash function returns a 0, purple hash function returns 6, and so we go to our bit array and make sure those index positions 0 and 6 are set to a 1. So you can see that they're both set to 1. Bluey, something similar. Both the hash functions see it. They return a value of 3 and 4. We go to our bit array, set those values to 1 as well. Bingo is now we get a value of 7 for the first hash function, a value of 10 for the second hash function, and we set value to 1 in both those areas. Now here's the thing about for bingo though. Notice that for bingo, return a value of 7. In the bit array, that value has already been set to 1, and that was set to, according to this particular arrow, by ing at the very beginning. That's okay. Whenever that happens, don't worry about it. Just keep this detail in mind, but whenever that happens and the value is already set to 1, it's so cool. Just move on. Don't worry about it. The next value is for pixel. The hash functions we have return 1 and 10. 1, the index position 1, the value there is set to 1 now. And for 10, it's already a 1 from when bingo was stored just a second ago. So it remains a 1. So all pixel and all of the values we want to store are now represented in our bit array. And so at this point, we have all of our initial values represented in our bit array. And as a recap, what we did was we took each item, passed it through both of our hash functions. We mapped the return values to the appropriate position in the bit array, because the return value is an index position, and we ensured that the bit array value at those positions is set to 1. So nothing too complicated yet. And so if we simplified everything down, our Bloom filter is nothing more than this. You have the hash functions, and then you have the bit array that is not populated. The original data that we started off with, the values for all the pets and the usernames that we had there, that's no longer needed because that value was used to populate our bit array, and right now that value is now represented as a series of 1s and 0s mapped to the appropriate index position. So when I mentioned earlier, a bit array stores a fingerprint of the data, not the actual data itself. That fingerprint is what you're seeing here, the 1s and 0s. The actual data is now gone. No need to keep that around. It could still be in a database. It could do whatever needs to be there. So once we have our Bloom filter, once we have the initial data fully populated inside of it, what we do is the most common thing a Bloom filter is used for, which is to check for a value. Does this username exist? And so now that we have our initial data, now we're going to check whether a value exists in our Bloom filter or not. And the way we check for a value is by passing it to the same hash functions and mapping it to what is stored in the Bloom filter itself. And so for example, let's say I want to check for the value Scooby-Doo. So username Scooby-Doo was entered. I pass it into my two hash functions, the same hash function I had before, and the blue hash function returns a value of 4. The purple octopus hash function returns a value of 8. And so the hash function for Scooby-Doo is 4 and 8. What do we do next? We go to our bit array and look at what value is stored at index positions that are returned by the hash function. So at index position 4, our bit array has a value of 1. Okay. At index position 8, our bit array has a value of 0. So when we get into a situation, when we see a 0 at any point in our bit array, that means this item was not stored originally from our initial set of data that we are creating. And so in this case, Scooby-Doo is not in our database, because whenever the result of a hash function points to a value of 0, the outcome is 100% straightforward. The item we were checking for is absolutely not a part of the larger collection. And so whenever 0 is encountered, again, this is important, 100% guarantee that that item is not a part of the collection. So we can basically save a whole lot of time. So I type in Scooby-Doo, I want to register, then I go to the Bloom filter. The Bloom filter is like, yep, Scooby-Doo is not a part of the giant database of usernames. Then I don't have to go check it because the Bloom filter already contains the mappings of zeros and ones that tell me that. So the value is no. And I can go and register. And this was done very, very quickly because I never had to go and search the full database itself. So pretty awesome, right? So it doesn't matter if our Bloom filter happens to have 99 hash functions. 98 of those hash functions said, this is good, everything is fine, but one of those returned a 0. If even one hash function returns a value of 0 from all the hash functions we have for the same value, the item is considered to not exist. It's not a popularity contest. Every single hash function needs to be consistent in the value it is giving. And so in this case, because we had one value giving a 1, but the second hash function gave a 0, the 0 wins out, and therefore the answer is this item is not in the larger collection. So now let's check for muffins. We know that muffins does exist because it was for the 6 items or 5 items we stored earlier. I'm going to go through the same hash functions. The values I returned are 0 and 6. Now, the important part to remember is that the hash functions we have are not going to give a different result for the same value that's being passed into it. One of the core part about hash function is that it's consistent, the values it gives. So when we stored muffins earlier, we returned a value of 0 and 6 from both our hash functions. And right now, when we're checking with the value of muffins, we get the same result. We get 0 and 6 back because our hash functions are not changed, they remain consistent. Otherwise, they will not be considered hash functions. When we look at our bit array at index positions 0 and 6, the value is a 1, which means that the item exists, right? And if you recall, muffins was something we stored earlier. Now, the return values then were, this is reiterating that the hash function has the same value. Now, when we have a 0 and 6 and a 1 is returned, it's reasonable for us to say the answer is going to be yes. Does the item exist in a larger collection? Is muffins a part of the database? Yes, it is. But is that actually accurate? So, as it turns out, there's a bit of a gray area here. So when we get all 1s, the Bloom filter is not going to say with 100% certainty that the value actually exists. Does the item actually exist? It's not a clear yes, because a Bloom filter, all they can do is give a high confidence answer that the item does exist, but we will need to actually check the source, the giant database of usernames, to be 100% certain. So the answer is more of a yes-ish. It's probably a yes, but we cannot guarantee that, so you need to double check anyway. And the reason is that a Bloom filter is known as a probabilistic data structure. All the data structures we've seen so far are deterministic. They do exactly what they say they're going to do. There's no and, ifs, or buts about them. But the Bloom filter is not quite the same thing. It has a bit of some fuzziness to it, when it gives an answer, and it's probabilistic because we can control the probability a bit, so it is not 100% guaranteed, but maybe 99.9% accurate or 99.99999% accurate, but it's probabilistic. It's not 100%. And so what do we do here is, because we got values of 1, which seems to indicate item exists, but we can't say with certainty, we check our Bloom filter. We know we got a 1 across, but then we go to our giant database of usernames, step 2, and then we search a giant database. They'll return a yes or a no. In this case, we know muffins does exist, so we get a yes, and we are able to notify the user and say, sorry, muffins can't be picked as a username because it has already been registered. You need to pick a different username. Now, we do this because Bloom filters are prone to generating what are known as false positives, where they may say an item exists, but in reality, that item doesn't. And this happens when an item that was never added to the Bloom filter hashes to positions that were previously set to 1, by other elements. And we saw that a few times already, where when we were adding the items initially, the value in the Bloom filter in the bit array was already set to 1 by another item before it. So it's kind of hard to know which item did this or did not do this. And so, for example, let's say we're checking for the name Rusty. It says username Rusty available. When we send this username to both of our hash functions, the first hash function returns a 1, the second hash function returns a 5. When we look at our bit array, the index positions at 1 and 5 are set to 1. So according to what we saw earlier, this probably means the item is going to be set it's already in our database. So that's probably a yes. But when we actually search for it, in this case, our giant database of usernames is just the 5 names that we stored earlier, the names that we of the pets, Bluey, Bingo, Ingy, Pixel, and I think Muffins. And so when we check for Rusty in this case, our Bloom filter is like, yeah, probably there. So go check the real database. We go to the real database, and we find out that Rusty is actually not one of the usernames there. So it's actually a no. And so it goes back, and we now are able to say Rusty, the username, is available. And this is an example of a false positive, because our Bloom filter seemed to indicate the item clearly existed, but the reality is it did not exist in our database of 5 usernames. And so what Bloom filters will do is this: they will definitively let you know if they haven't seen something before. So if the item does not exist, they will very quickly and with 100% certainty say it does not exist. They cannot say with 100% certainty, they cannot say definitively if they have seen an item, if an item does exist. The best they can give you is a high confidence yes. And that's the magic behind what makes Bloom filters so effective when dealing with large amounts of data, is that they have this bit of a hand waviness to when something isn't going to be right, which you need to optimize for to make sure you don't do that. But on average, if the item is no, it's a very fast yes. The item does not exist. And so this lack of definitiveness in saying yes is what makes Bloom filters a probabilistic data structure. Now, what we can do though, right? Yes, that's not the most ideal situation to be in. You want your data to be always accurate. When you're asking for something, you don't want someone to say like, maybe, that's probably the worst answer you get. You want to get a yes or a no. We can't do that. If you want that, hash tables, arrays, lists, and you had to pay the penalty in memory and performance and other things. What we can do though is make sure our Bloom filters say the right thing quickly in more situations than not. We can optimize them. And there are 3 values that we can adjust. The length of our bit array, which you'll often see represented as M in formal textbooks and in formulas and other analyses. The number of hash functions, which are often represented as the letter K, and the false positive rate, a percentage value or decimal value, represented as P. Now we're going to walk through all 3 of these things and walk through an actual example as well, just to cement how it all works. So for the optimal bit array size, you have a formula. And this formula is the number of items, which is stored by n, and then the probability value, and that's just squared, and the typical mathematical from a natural log to a squared. So one of the biggest deciders of the bit size is, besides the number of elements you have, but you can't change the number of elements you have. So that just ignore that. It's a constant. Your data is your data. Is the value for p, which is the positive probability value. That is the value in a range of 0 to p to 1. A value of 0 will never going to happen, because that means that you'll have a perfect score, which you'll never get a perfect bit array with an infinitely large bit array where you will never get a false positive. And there'll be a 1 where you'll have everything's going to be wrong. You don't want that either. So, you'll be somewhere in the middle. And the typical values for P are 0.1% to 10%. So you'll see either 0.001 or 0.1. And 0.01 though, 1%, is most commonly chosen because that balances space efficiency and accuracy. So you're not getting a very memory intensive Bloom filter, but also not getting one that is going to be wrong more often than not. And the lower values, of course, close to 0 provide better accuracy, but they require more space. And higher values closer to 1, they save space, but they consider as false positives. And if you go back to this equation, you can plug those numbers in to see what would be a small value and a large value for P, and see how it adjusts the bit size. You can get that very quickly. The next value is the number of hash functions. That's another variable we can control. This is a much simpler formula. It's just m over n multiplied by the natural log to ln of 2. And the hash functions, again, it's a balancing act, because if we have too few hash functions, the bit array will be kind of underutilized, leading to higher false positive rates because fewer distinct bits are set per element. It also means that it's more likely that a specific combination of bits to test whether an element exists will probably be quickly set by other elements itself. So it's not exactly going to be a very accurate one. For our 5 elements, we had 2 hash functions, but one could imagine if you have many elements, you might have more, or maybe not a whole lot more, and we'll talk about that more in a second. But if you have too many hash functions, it means your bit array becomes saturated way too quickly. If you have, let's say you have 1,000 hash functions and your bit array is 1,000 items in size, after a few items, each of those hash functions, unless they're all colliding and pointing to the same value, are going to pretty much start putting a 1 in all empty parts of our bit array. So it's not really great. And then the more hash functions you have, the more computationally intensive the operation for storing a value or checking a value exists just becomes. And so ideally, the optimally chosen K minimizes the false positive probability for a given bit array size and element count. And in most cases, what we're going to find is that the number of hash functions used, even in major large-scale production, scale Bloom filters, is a value between 3 and 10. So K of 3 or a K of 10, or any value in between that, is what most Bloom filters will have for the number of hash functions. So now let's look at an example, because that was a pretty abstract thing. I just gave out a formula, like examples. Let's say we have a database of usernames, going back to our pet book, and it has 10 million entries. So our end value is 10 million. And what we want to do is we want to have a Bloom filter to quickly see if a username we're checking for already exists or not. And our false probability rate is 1% or 0.01. So 1% of those things we're looking for, we might need to go to the real database to do a big check. So the optimal bit array size, if you plug in all these values, n is already 10 million, p is 0.01. And so when we go through the math for all these things, you'll see that, in step 2, all the values are plugged in. Then it becomes 10 million times minus 4.60517 divided by 0.48453. You can see it on the screen. I'm not doing mental math, but I'm just looking at these values as they are. And then once you do all the calculation, our bit array size, or optimal bit array size, is around 95,850,583. That's a pretty big bit size, but for 10 million elements, maybe not that much. And the number of hash functions is K, the formula we saw earlier, m over n times the natural log of 2. So that's m is 95 million. We divide that by 10 million number of items. That just becomes 0.6931. And then our number of hash functions is approximately 7. So we get 7 hash functions is what we need as the optimal value based on the formulas that we have right now. Now, the thing was about storage for a brief moment, because I talked about storage, I talked about hash tables and hash functions. Hash tables and sets, and they're similar, cousins as being memory intensive. The Bloom filter has a bit array of 95.85 million bits. That's about, number of bytes it would be. You divide that by 8, you get 11.9 million bytes, which is around 12 megabytes. 11.99 million bytes, so it's around 12 megabytes. An equivalent hash function, though, for the same amount of data, would take up around 240 megabytes of memory. And I actually talk more about the math behind how the hash function stores data and why it is 240 megabytes in the article, Bloom Filter, a deep dive. So the link for that is in the video description below, because the video I'm showing right now has a more detailed article form as well. And in that one, I go through the math in great detail on how much memory it takes and how a hash table operates to end up with 240 megabytes. I don't include that in this video because this video is already pretty long, and so I don't want to make it even longer, especially on a detour where you just want to know if a hash table truly is more memory or less memory efficient than a Bloom filter is or not. So now let's talk about the performance of Bloom filters. We talked about Bloom filters being pretty performant overall, especially when they are going to very quickly tell you that an item does not exist. And so if you look at, there are two actions here. There's insertion, there's the query, the checking operation. In all cases, the speed of a Bloom filter is big O of K, which is sort of misleading. I'll talk to you about that in a moment. But in all the literature, and everywhere in your classes and in interviews and so on, the answer is always going to be big O of K. And K has to do with the number of hash functions that are available. Each hash function takes a constant amount of time to operate. And so you want to make sure how much your hash functions run. So the more hash functions you have, the slower your overall function is going to be. So big O of K. Now, when we talk about Bloom filter performance, the focus is always on the red square right here, which is what you're trying to do and the Bloom filter's own mechanics of how it operates. And so that's where the big O of K comes from. It never includes the times when you have to go to the actual data source and do a query on the larger data set. It could be, could be a database, it could be something, it could be a physical hard drive on your local machine, it could be something else. That is not included as part of it. So the total time is often big O of k plus the actual time, in cases where an item does not exist, to find it. But that's never included, so just keep that in mind. But we're not like that though. We want to make sure that you're also able to use these in the real world. So what would an idea for big O of the, searching a database actually be? There are 3 values here, because your database could be implemented in one of 3 approaches. One is it could be a hash table. And if it's a hash table, it's just big O of 1. Your giant database of usernames is literally a hash table. And so you go from big O of k, then it's big O of 1 from there. So it's big O of k plus big O of 1. It could be an index search, which is a very common way of searching through data, and that's often implemented using B trees and other data structures behind the scenes. That's big O of log n. So that's a slightly slower approach than your hash table. And of course, the worst possible way of searching a database that we saw at the very beginning is you do a full table scan, which is a list or an array where you sequentially go through the items. That is big O of n. It's linear time. So it would be big O of k plus big O of n for being able to use a Bloom filter in the real world. And of course, we can't just work in isolation. It's not a vacuum in some cases. You have to add in some disk and network latency for completeness. So all of these things might have an extra bit of noise that makes them a little slower than what is currently advertised as a sticker price. So with that, we covered a lot of ground here. We started off by talking about how Bloom filters are very popular and are used in a billion different situations in everyday life. And the reason is that it's a space-efficient, probabilistic data structure designed to very quickly test whether an element is a member of a set or a collection, and it is lightning fast because it only stores a fingerprint of the data being asked for. And it's also lightning efficient from a memory point of view because it only stores a fingerprint of the data. The data could be in your hash table, your actual source could be a blob of multiple megabytes of data, but all that's stored in your bit array is a 0 or a 1, which is very, very efficient. And the downside, of course, is that it's not deterministic, hence being a probabilistic data structure. It has a bit of fuzziness in how accurate its responses are. So you need to be willing to, definitely be celebrating its performance and memory efficiencies, but also keeping in mind that there will be times when it might say an item exists or an item does not, item exists, but it actually doesn't. So you have to do a very slow lookup to get these things right. Trade-offs. As with all things in life, it also applies to data structures and algorithms. With that, if you have any questions about a Bloom filter or any other topic that you want to discuss, whether it's web development related or whether it is data structures and algorithms related, the best place to go is the forums at formatgroup.com, where I and others will be very happy to help you out. You have a friendly community willing to answer your questions and just be a fun group to learn from. And of course, if you like this video, comment, subscribe, tell your friends and enemies all about it. Sign up for the newsletter to get updates on various things I focus on in email form. And for bite-sized updates, follow me at Krupa on Twitter, or X as it's known these days, and other social networks where at Krupa refers to me. And lastly, I write a bunch of books, not just on data structures and algorithms, but on animation, React, just core JavaScript fundamentals, and a bunch of other topics that I find really interesting and hopefully you'll find interesting to learn from as well. Links to all of that below in the video. And with that, I'll see you all next time.